If the speakers would like water, there's water off to the side there. So, Tilman, over to you.
Thank you. Good morning. Somewhere's full screen here. Yes. So, good morning, everybody. I wanted to talk a bit about the Digital Music Lab. That's an HRC-funded project about developing methods and tools for analyzing big music data. So. This is the outline. Maybe I have a few too many slides, so I'll try to be quick, but please ask questions anytime. So the objectives of this project are to develop and evaluate music research methods for big data. So that includes musicological aspects, but also the infrastructure for large-scale music analysis, software and hardware, and the interfaces for plugins. And so in effect, we want to develop tools for large-scale computational musicology and also produce or at least make available large music data sets. As you can see on the right, we have actually 4 partners in the project. It's City University, where I am with the Music Informatics Research Group. That includes Emmanuel Benetos and Daniel Wolf. From the musicology side, there is Stephen Cottrell and Dan Tidder, and we also have a specialist on visualization, that's Jason Dykes. From Queen Mary, it's Mark Plumley and Simon Dixon and Mathieu Bartet. And from UCL, we have Nicholas Gold and Samar Abdallah. And the British Library with Mahendra Mahi and Adam Tovel. So it's a lot of people, and with different expertise, different backgrounds. We're trying to have a truly interdisciplinary collaboration to make something that works both from the technical side and also for musicologists. So the musical focus is on performance research, including automated score and audio analysis. And then on top of that, we need some kind of a collection level analysis, so starting with basic statistics on the collections that we're analyzing. We're looking at genres, in terms of genres, mainly at classical, folk, world, and popular music. That's for pragmatic reasons, partly because for classical music there are MIDI data often available, and folk music tends to be more monophonic or less polyphonic, which makes it easier to transcribe. And the research questions in this context for us are, how can big data be used in music research? How can we employ audio transcription and alignment to produce performance analysis on a large scale? And what's the infrastructure we need for that, and how can we provide it? And also we want to try and make these tools usable for music research and musicians who are not necessarily experts in programming MATLAB or Python. So we're collaborating with the British Library, and the British Library has a huge archive of audio recordings, but many of them are not available at all to the public, or they can only be listened to in the reading rooms, but not actually be analyzed. So actually, it's over 3 million tracks, and only, I think at the moment, you can access about 30,000 over the web. So we're trying to make more of that material accessible. There is, as always, an issue with copyright. So we're trying to work around that as far as possible by enabling analysis, even if the audio can't leave the building. So then the audio has to stay on the server, but still we can provide interfaces to enable analysis remotely. And the other big data set that we're working with is provided by our partner iLikeMusic. So they have about 1.2 million commercial music tracks and about 400K production music. And they also give us access. Again, we cannot distribute the audio, but we can allow people to use the derived data and run analyses with their own parameterizations. So here's a bit an overview of the iLikeMusic data that consists, well, here's a large proportion of rock and pop, but there is also a substantial amount of folk music, for instance, some jazz, and although that's as a proportion of the whole set is not too much in comparison to other sets, these are actually quite big sets of tracks. As a starting point, we're using Charm because the establishing access to the large collections is a slow process. So to develop our methods, to start and to get going, we're using Charm, which is a smaller data set, about 5,000 recordings, and which has some metadata associated with it, which is also useful. And so the main things we want to do are to use automatic music transcription, or where applicable, score to audio alignment and chord and key detection, to provide some basic data that is useful for musicologists. Then we can apply things like voice separation, structural analysis, or melodic analysis. And the idea is to integrate the audio and symbolic analysis, or at least to enable the integration, and then aggregate the results per track on or per piece over larger collections to detect trends and well, patterns that we're looking for. Of course, audio transcription is not perfect, especially not if the material is polyphonic and or noisy. But that is something we need to find ways of working with that. I mean, we can still, well, we hope we can still find meaningful and significant results despite the noisy data. But that is a general problem when you deal with large data sets. You usually have a lot of noise. So I probably don't need to explain to you what automatic transcription is, so I'll skip this slide. And score to audio alignment is pretty much, it's very similar, only that we kind of know what the score is and try to align it rather than transcribe. And so what we're already doing, well, we have done audio transcription on Charm, and we have also already run chord detection on the ILM data set. So that was already quite a large-scale analysis. We're using VAM plugins, so in this case the Chordino VAM plugin from this place here. And we're also going to work on Shankarian analysis, or at least structural analysis. That's going to start soon. That's what our colleagues at UCL are aiming to develop. So the whole infrastructure consists of software and hardware that we're setting up to enable distributed parallel MIR processing and also data storage. And the idea is that we can preserve and sustain music research by well, providing access, but also then storing the results of the different steps of the music analysis so that they can be reused. Because otherwise, if you want to analyze a large audio collection and you want to transcribe everything, that can easily take weeks, depending on the size of the collection and the processing power. So it's important to try and store as many results as possible and to enable reuse and sustainability. Also, as I mentioned already, support for remote analysis so that the audio stays on the server is important, because otherwise most large collections are not accessible. Most of them have copyrights attached to them so that you cannot just download the audio. In terms of hardware, we are in the process of acquiring and installing 2 servers. One will be located at the British Library and at iLikeMusic, and they have to be physically located there because otherwise we couldn't get access to the audio data. These are fairly decent-sized servers, 20 cores, 128 gigabytes RAM, and they will connect to a web server where then it will be possible for researchers to submit their queries. The techniques we're using are basically standard big data setup at the moment, like Hadoop. We'll run it in a virtual machine. That has partly to do with the existing infrastructure. It's not necessary, but it has the advantage that we can actually set up the whole system on a virtual machine. Once it's been tested and tried, we can then distribute a virtual machine image for other people who want to do the same thing and do analysis in-house, or actually offer services to others so that we can connect different data sets across different sites. So the main tools are, the main programming language is Python, and we'll, as I mentioned, WAM plugins are supported. We're also looking to support for other plugin formats. And, well, then basically in this map-reduce scenario, the mapping step describes the analysis of the individual tracks, and then the reduce steps is the collection level analysis. That's at least how we think of it at the moment. Is that a question?
Yeah, it's a good question. Can you tell me a bit more about iTunes?
Personally, I can't tell you very much about it. Daniel has done the work. Is he not here? No.
We can talk about that.
Sorry. Yeah, so, well, as far as I know, it's a Python wrapper for Hadoop, but I don't know more details than that myself. Daniel Wolf is the person to ask. Yeah, so in terms of supporting sustainable research, we have a preference for open source. We try to make everything open source as far as possible, and we're using repositories to make our own software available, and to also the data and the experiments we run. And yeah, as I already mentioned, we want to try and provide this whole setup so that other institutions can easily then run it in a virtual machine on their own machines. Part of the project aims is to make sure that what we deliver, or what we do, is what researchers actually want. So we held a workshop 19th March with researchers from different backgrounds, so musicologists as well as music technology people, and try to find out what people would want from such a system. And we found quite a diverse range of questions relating to MIR access, to context, and to actual performance, music performance research, going deep into music psychology, so broad spectrum. And we try to then sort them by priority and feasibility, and I'm not going to go through all of them in detail. The good thing is we found that in the end, at least half of the top 10 tasks in terms of priority, we also found to be in the top 10 of our feasibility ranking. So we do think we can do some useful things here. So including, well, obviously training algorithms on large data sets, and I think the top priority was doing automatic analysis of scores and of audio and combining that. Those are 1 and 2. Automatic analysis of scores is, of course, a bit of an open problem, so it can be feasible depending on what you exactly expect from it. Yes. So a few things that concrete problems that we're working on at the moment. One is a data set definition. So if you want to run an experiment on a large collection, one of the problems is Thanks. You need to identify which tracks you want to analyze, or at least you often need to label them to then find out differences or trends. And manually labeling 1 million tracks is not really feasible unless you have a lot of money to pay people to do it, but that's not the case for us. So we're looking into semi-supervised annotation and try to find a way of efficiently labeling data with as little labels as possible, so to have not too much human time spent on this. So what we find at the moment is with active learning using uncertainty sampling, we can find actually pretty stable classification rates of 2 or 3% depending on what method you use, from 55 to 150 labels onwards. So actually it is possible to do the labeling with a really small amount of human labor. And to make that a little easier, we've created a little user interface that kind of gamified the task, which should A, make it a bit more fun, and B, make it also, well, give us some control. It should incentivize the agreement between users, because that's what you get points for in the game. And also, we have built in some tests that whether people are actually paying attention well when they fill in this, when they play this game and fill in the forms. Another piece of work that's been ongoing at the moment is extraction of chord sequences. So there is already one server installed at ILM from a previous project that has already been used by Mathieu Bartet to extract chord sequences on all of the ILM dataset. And we're currently looking into, well, analyzing that. We find that we're lacking key information, so we next step is to run key recognition on this. It's a pretty slow process. Took 6 weeks, by the way. This whole thing, we hope with the new service to speed that up and with better parallelization. So the next step then for us is to see how we can analyze this. So this is looking at sequential pattern mining, trying to find the most frequent transitions, and how can we make that useful for musicologists who might not be used to reading graphs like this. So the next question that we're going to tackle with Jason Dykes is to look at visualizations that make the analysis of these results easier for musicologists. So, well, to come to the conclusions, that's at the moment most musicological research is limited to small data sets, but we feel that it can benefit from larger data sets, and we're working on making the tools to enable that. And all the tools that we're developing and all the results will be made available to the research community and users. And so we hope that we will be able to present something to you and make available to you later this year. So if you have any questions, come to, or if you want to see what we're doing, come to our website. And yeah, that's it for me. Thank you.
Okay, questions, Sasha?
Yeah, so I work for Audio Analytic. We're doing software for recognizing sounds which are not necessarily music, any type of environmental sound. So I'm interested in knowing what proportion of this infrastructure is specific to music and what proportion could be applied to the classical sound processing problems of labeling, then machine learning things and all that.
Well, I would say this one thing that is music-specific is the VAMP plugins. So insofar as they are music-specific, this system is music-specific. We're also looking into using TimeSide that Jung will be talking about in a minute, which enables other plugin formats, or if you write your own analysis algorithms, then of course you're more flexible. I think on the collection level analysis there isn't. Well, I think there is not too much that is music specific. So I guess it would be pretty much. You could use pretty much the same setup. Yeah.
I'm wondering about how you determine what to focus on from a sort of supply and demand point of view. In other words, are there sort of particular musicological questions that you're hoping to be able to answer using this data, or are you hoping to open the ground for new questions that you don't know what they are yet?
In a way, both. Well, we're looking at some concrete questions. That is, we're looking, for instance, at pitch levels, pitch drift, temperament. That is, well, because that's relatively straightforward to do. That similar things have been done in the past, but we're trying to do that on a larger scale. And another thing that seems to be of interest is to look at the timing of performance. That is a bit more difficult because the transcription is typically doesn't have very precise timing information. Another question that was asked relatively often is to do structural analysis on the audio. So there are established audio methods with similarity matrices. To do that on a symbolic level, well, our colleagues from UCL are going to work on that. So these are the concrete problems we are looking at the moment. But we will hope that with larger data sets you can also try to answer new questions, like maybe you can find evidence for different schools of performance, or evidence of differences or similarities between different cultures that are perhaps not so easy to find if you have small data sets, so because you don't get significant results.
A question about, you mentioned about sequential pattern mapping. Can this process be parallelized?
Yes, to some degree. That is, well, Matthias, I'm not sure which algorithm exactly you used. So
Sequential pattern mining, not mapping. And there are some framework where these things could be parallelized, yes. And for instance, the R framework for statistical analysis, and where there is a large community of people developing new tools for R. So you have some modules to parallelize things in R, and there are some sequential pattern mining algorithms which are implemented in this framework. There is also VECA, the VECA framework. Yeah, so it's certainly possible.
But I guess also there's basic parallelization from the fact that you've got multiple tracks that essentially you can do independent analysis.
So the parallelization happens at the analysis stage to get the features, the chord features in this case, but it could be other types of features. But once you have the features and you want to apply some of the techniques of analysis like sequential pattern mining or something else, you could also parallelize that. If you have 1 million chord sequences, then you might want to parallelize the sort of processing you do with that.
I mean, that's our general approach, that the processing of the individual tracks for feature extraction, which is typically the first step in any analysis process, that can be easily be processed by processing everything, parallelized by processing every track separately, and then depends on the type of analysis you're doing, what degree of parallelization you can achieve.
And one last question, I think, Dan.
So yeah, obviously, analysing a single track can be trivially parallelizable. Like some things are really quite difficult to scale, like similarity search. So naively, you've got n squared in the number of, because you've got to analyse every pair. For issues like that, are you basically just throwing a lot of computers at it, or are there cleverer ways to do things like that?
Well, we're not. There are, I think, cleverer ways for doing that, but that's not really what we're working on in this project. We don't have it's a relatively short project. We don't have the resources to do too much original research of that nature. But I think there are people working on these problems. So we hope that others can contribute here.
Okay, so I think if there are any other questions, we can have them over lunch. So thanks very much again, Tilman. Thank you. And our next speaker up is Bob Sturm. While Bob is finding his